Today I'm here to talk to you guys about higher kind of types. This talk was in part motivated by what I hope were tongue-in-cheek comments by a lot of my friends and coworkers about languages that are coming out like Java 8 with first-class functions. And these comments generally went along the lines of, well, Java 8 has first-class functions, so there's not really any big reason to use Scala now, right? Especially because so many more. Is this better? Is the mic on? Maybe it's not on. Is this better? OK, there you go. Cool. A lot of my coworkers like Java 8 is out. There's not really any reason to use Scala. And for me, that's frankly not true. And I'm sure for many of you, that's not true. What Scala has to offer, I think, is much more than just first-class functions. First-class functions tend to be sort of the baseline against which I measure languages. When I look at a language, I sort of expect it to have first-class functions at this point, especially languages that operate at the scale or at the level that Scala does. And so one of the big things that Scala offers in terms of features is higher kind of types. And this is a feature that I don't see in many other languages, but I find extremely useful. And I'm spoiled by them at this point. So many times when a coworker tells me about, oh, have you checked out this language, one of the first things I go look for is higher kind of types. And sadly, more often than not, it doesn't support it. So my goal in this talk is to introduce higher kind of types and motivate why we should care about them. So to get a sort of feel for the room, how many people have used future.sequence or future.traverse from the standard library? Yeah, a lot. So one of the most common questions I get both at work and in IRC and in Gitter is how do I do something like future.traverse, except instead of future, I want to use option, or I want to use try, or I want to use either. And so it turns out, let's see, can everyone read that? Can everyone read the screen here? It's all good. So I have a simplified version of the future.traverse here. So for those who don't know, future.traverse is sort of like a scatter-gather thing. You have a list of A's and a function from A to future of B. And what it does is it takes every single element of the list, it forks off some computation, and then gathers all the results into a future of a list and then returns. And a lot of times people want this same behavior, except instead of future, they want to do something like option or use either, where they're doing something like validating a dynamic list of inputs, right? Some user input, and they want to run some validation function against it. And they want to do this with other data types like I/O and state or whatever. But it turns out the standard library doesn't provide this, as far as I know. And you could actually go off and write traverse for option, traverse for either. And at one point, I did have like a single file at work that was just traverse option, traverse either. And when you do that, you'll quickly see that the code is largely the same. So similar that it's kind of screaming for like abstraction. And it turned out this abstraction is you can only really encode this kind of abstraction if your language supports higher kind of types. So to give sort of a sneak peek of how this function looks like, I'll just go ahead and write it. So I'm going to write a traverse that's parameterized over some f, right? So this f is going to take the place of the future in the standard library. And other than that, it's going to remain largely the same. So we're going to start. That's going to bother me. We're going to start by folding over the list. And we have nothing to collect so far. So we're going to start with an empty list of B's. We're going to lift it into whatever this f is. So if f is future, we would start with a future of a list of B's. And the function is going to expect the next A in the list, the accumulator we have so far. And we need to return another f of list of B. So we can do that by first applying the function to A. Then we can tuple that fb with the accumulator we have so far. And then we can map over it by prepending the first element with the second element. Cool. So now what we can do is we can take a list. And I'm going to traverse over the list. And I'll do something like future I times 2. And this will give me a future of a list of int. So that works, right? So now we're at feature parity with the standard library. Now we can use the exact same traverse function. And I can do something like if I mod 2 double equals 0, sum of I divided by 2, else none. So this is sort of like a dummy validation function. And this will give me an option of a list of int. So it's the exact same traverse function. but I'm swapping in, instead of future, I'm going to use option. And we can also do something like this. Maybe if I w equals 0, left, oops, else right of 1.0 divided by I. And this will give me an either of a string of a list of double, I believe. And the compiler actually needs a little bit of help at this point. So I'm going to annotate the types. And that works, right? So we're seeing we've written traverse once and for all, and we're able to plug in whatever types we want. And it turns out that in order to write this traverse this way, we actually need our language to support higher kind of types. And so in languages like Java 8 that don't have those, we actually couldn't write traverse, at least not easily. So I'm going to try to introduce higher kind of types now. To sort of give motivation for why we care, I'm going to first talk about things at the value level. So in many languages, we have two separate notions between values and functions. Values are sort of things that we can assign to variables, things we have a hold of, we can pass to functions and get values back. And then in a separate world or a separate universe, we have functions, which aren't values, but they're able to take values and produce values. But functions themselves aren't values. And so in these kinds of languages, we quickly run into certain situations where we can't talk about things we want to be able to talk about. So a very simple thing is if I have a collection of elements, I want to apply some function to each element to get a new list, right? And I'm using recursion here, and in many languages we'll just use like a for loop. And this has become so natural to us that we know it's like code duplication, but our eyes sort of like see through all the noise and see what we want to do. So in this case, I'm just doing something really simple. I'm just taking each string and duplicating it. In another case, maybe I want to take each character and get the integer code associated with it. And then in some other case, maybe I just want to check if the integer is equal to 0. And you can see that the code here, the code remains largely the same. And the only thing that's really changing is what function we're applying at each element. And we'd like to be able to say we want to write this kind of this traversal once and for all. But in a language without first-class functions, we wouldn't be able to say, give me a function as an argument, and I'll apply that function to each element, right? So we end up having to either do a lot of duplication, write the for loop multiple times, and that's not good. So of course, in Scala, we do live in a language with first-class functions. So we are able to write this kind of thing, map once and for all, and say, give me a list of a function you want me to apply each element, and then I'll go ahead and do the thing you want. So without first-class functions, we wouldn't have been able to write map, right? At least not in a nice or easy way. And we can write all the previous functions in terms of map, but usually this is just so simple that you would just inline it instead of defining it this way. A similar situation, we run into a similar situation at the type level, right? So now we're going to go from values to types. In many languages, we have a distinction between proper types or fully applied types or what's called types of kind star. And then we have sort of functions at the type level or type operators, functions so you can think about type constructors, which are things that take a type and produce a type, right? So these are sort of like functions at the type level. And again, in a lot of languages, we have this distinction. And just like in languages where we don't have first-class functions, we run into problems where we want to be able to abstract away something, but we're not able. The type system doesn't give us the feature that we need in order to talk about these kinds of things, because we have this separation between fully applied types and type constructors. So here's the implementation of traverse future, right, where we're specifically traversing the list using a future. And if you compare this to the code I wrote at the beginning of the talk, it's largely the same. We're going to start with an empty list, lift it into a future, take two futures, zip them together, map over it to prepend, and we're done. That's the code for traverse option. There's a little bit of noise just due to the way zip works on options in the standard library, but it's largely the same. Lift into option, zip, map. And there's traverse either. So you can see at this point, like, the code is pretty much the same here, right? The only thing that's changing is how we're lifting it into whatever f we choose. We need to be able to zip them together, and we need to be able to map over it. And so we want to be able to abstract that notion out and allow users to sort of tell us what f they want, and just write a traverse once and for all. And so there's an abstraction that exists that's very useful called applicative. And this is where the importance of higher kind of types comes in, right? So applicative sort of encodes the three operations we need. We're able to lift some a into f. We're able to take two f's and tuple them together, and we're able to map over it. And if you look at what applicatives parameterize over, it's not something like a list or a vector where it's a list of A or a vector of A. Applicative takes it as an argument, a type constructor. So this is sort of like writing a function that takes as an argument a function. And you can see this when we implement applicative for future or for option or for either, where we're not saying I'm defining an applicative of a future of an int. I'm defining applicative for future, the type constructor itself. And with applicative in place, we can write traverse once and for all, right? Just like what we did in the beginning. And so where before we had map, for map we gave it a function that allows us to plug in the behavior we want. For traverse, we're giving it a type constructor that allows us to define how we're doing the traversal over the list. And just like with map, we're able to define all the various traversals we want, because traverse is usually, these are sort of trivial, and indeed for future and option, and it should be the case for either. The definition is the same. These are usually just inlined, right? So now we're able to talk again about abstractions that we otherwise would not be able to talk about without higher kind of types. So I've mostly been talking about traverse, mostly because that's like by and large the most common solution to many problems I see. There's sort of like a joke in a lot of IRC and Gitter channels I hang out in, where if your question starts with I have a list of something, the answer is probably traverse. And it turns out often enough that that tends to be the case. But now I want to show you guys some other examples, because I don't want to say like the whole reason we care about higher kind of types is just so we can write traverse. We want to talk about other things as well. So let's see. Cool. So we have our friend traverse again. But what I'm going to do is I'm going to implement functions in terms of traverse. But those functions aren't going to be like the usual traverse option, traverse future that we've been talking about. So the first thing I want to show is map, a familiar friend. So map looks like this. Right? This is the map from the standard library. And I wanted to implement map in terms of traverse. And if we look at the type signatures of the two, they're kind of the same, but there's some slight difference, right? So both traverse and map take in a list of A's as an argument. The function that traverse takes is A to an F of B, whereas map just takes an A to B. And traverse returns an F of a list of B, whereas map just returns a list of B. So we need to, because we're implementing map in terms of traverse, we're able to pick what F we want. So we're in control of what F we choose. And basically, we need some F that encodes exactly as much information as what its type parameter is. And indeed, we could write a type that does that. And that's often called the identity functor, or just the identity data type. And if you look at the definition, it's pretty straightforward. It literally just wraps a value of type A, right? That's all it does. And it might seem pointless until you remember that applicative requires, as its argument, a type constructor. And now this identity data type is of the correct shape, right? Identity takes a type parameter and produces another type. It just doesn't do anything else beyond that. But with that in place, we can actually write an applicative instance for identity, right? So when you implement these three methods, Pure says, given an A, I want you to give me an identity of A, which is straightforward. To tuple together two identities, that's also pretty straightforward. And then map is the usual thing you would expect. Just get the values out, apply the function, rewrap it. So we got our applicative for identity. If we go back to that file, I can now say, I'm going to traverse over this list. And for each A, I'm going to apply F to it. But traverse wants an F of B in the end, right? So we need to pick some F to give it. So we're going to say, well, I'll just give you the identity. And at this point, traverse has given us, so it's an F of list of B, where F is identity. So now I have an identity of a list of B. I'm just going to get the list of B back out. All right, cool. So we've implemented map in terms of traverse. So that was cool. That means if our data type is able to define traverse, we sort of get map for free. Now I want to define a more interesting function beyond map. Map is kind of boring. So I want to implement this function, fold map. And fold map looks like this. A to B, B. So this looks a bit different. And I'm going to stub something out before I move on. Combine. So fold map says, given a list of A, and a function from A to B where B has a monoid instance, I'll return a B. And what a monoid is just basically, if B is a monoid, it means if you have two B values, you know how to combine them to get another B out, and you're also able to summon some constant identity value of type B as well. So fold map, basically, if the list is empty, returns the corresponding empty value for the monoid. And if it's not empty, it will apply the function to the first A, and then it'll just go along the list and just combine the B's as it goes along. And fold map's type signature looks very different from traverses, right? Traverse is taking an A to F of B and is returning an F of a list, whereas fold map is just returning a plain B. And at first glance, it seems like you won't be able to. We want to implement fold map in terms of traverse, but at first glance, it doesn't seem like this is possible. It turns out you can actually play some games with that F-type constructor that traverse expects. And without getting into too much detail, I'm just going to sort of give you guys the answer. But it turned out to be pretty interesting. We're going to use something called the const data type. And a const data type is also sort of dumb like the identity data type. The only difference is it has two type parameters instead of one. And the peculiarity is it only stores a value of the first type parameter. So the second type parameter exists at the type level, but it does nothing with it at the value level. And this might seem kind of silly and useless until we see what we're going to do with it. So we can define an applicative for const. That's sort of expected if we're going to call traverse with const. And the applicative instance for const says, I can define it if the first type parameter for const is a monoid. And what I'm going to do is just fix the first type parameter of const and leave the second one free, because applicative expects a unary type constructor, and const has two type parameters. This question mark syntax I'm using is from Kind Projector, which is a compiler plugin. So to implement this, we need to be able to take, given an A, I need a const of x of A. Recall that const doesn't do anything with the second type parameter. So really what we need is to conjure up an x value to put into a const. And the only way we can do that is through the monoid interface. So we're going to go ahead and just go monoid x.empty. To tuple together two consts, again, we're ignoring the second type parameter, right? But we do have two x values underlying these const values, and we need to return a new x on the other side. And conveniently, monoid gives us a way to do that, right? We just use monoid combine. Monoid x combine. And map, we have an x value. We have this function that we're sort of just going to ignore because we don't have an actual A to apply to it. So we're just going to get it and rewrap it. So the implementation is kind of weird. It seems kind of like we're forcing it into this applicative interface, but it actually ends up being really useful. So if we go back to the code now, what I can say is I'm going to traverse over this list. And for each A, I'm going to apply f to it. But now I'm going to wrap it in this const data type, right? So now f is fixed to what const is. And that will give me, at this point, it's going to be a const of a b of a list of b, which means it really just stores a b value because we only store something of the first type parameter. We just want a b, so I'm just going to go ahead and get it out. And the compiler needs a little bit of help at this point, so I'm going to annotate the types. Cool. So we've implemented two methods. So these are two methods implemented in terms of traverse. And we were able to implement these purely because traverse has this new parameter, this type parameter that we're able to play with. And a really cool thing is you can implement fold left and fold right in terms of fold map. And from fold left and fold right, you can implement all the various methods associated with lists, literally all the methods. And in a lot of functional programming libraries like Scala or Cat, you'll see that we have a type class that abstracts over things that you can traverse. And that type class is a subclass of functor, which are things that can be mapped over, and also is a subclass of foldable, which are things that can be fold mapped over. Which means that if you create a data type and it fits this traverse signature, if you can implement traverse for it, that means you get map and fold map for free. And by extension, you get fold left and fold right for free. And by extension, you get, if I can bring it up. Where's my mouse? Oh. You can get all these cool methods for free, right? All in terms of traverse, which I think is really cool. Because, again, this is all possible purely because we were able to talk about applicatives. We were able to pull out this generic traverse And we were only able to encode applicatives because of higher kind of types. You guys are all probably sick of Traverse by now, because I've been sort of talking about it for the last, I don't know, 10 minutes, 20 minutes it looks like. So I want to give one more example that's not Traverse related. I'm going to talk about DSLs. And so I'm writing sort of like a very plain calculator, kind of a very limited calculator DSL. And notice that this calculator data type is also a higher kind of data type because it's abstracted over a type constructor. And we're able to write programs in this DSL by doing something like this. We just write a program that takes a type constructor f, give me a calc of an f, and I'm able to write some program that returns an f of double. And after we write our programs in terms of this DSL, obviously we want the DSL to eventually do something, right? So at this point, we've just written some abstract program. We now actually wanted to do the computation for one, right? That's a pretty basic need. So we can write an interpreter for it. Let's say ID calculator. And I can use the identity functor that we used in the previous slide. Or not slide, but code snippet. So we need to be able to implement each method. So we need to be able to implement lit, which is pretty straightforward. We need to be able to add two numbers together, which in identity is easy. And we need to be able to take the square root of things. So I think that will be math.square root i.get.toDouble. All right. And I can get my final double out by calling the program with this interpreter, and then that'll give me identity of a double, and I'll just get that double back out. It turns out you can do another really cool thing, and this is something that I've actually done at work. This is running in production at my company, and I thought it was really neat, which is I can take that exact same program, and I can actually serialize it and dump it to disk without any changes. So I can write a serializer that extends calc. And here I'm going to use that const data type again, right? So that const data type doesn't really it turns out it's sort of like a dumb data type, but it turns out to be very useful. So here I'm going to use const, and I'm going to fix the first type parameter to be string. So string will be what I serialize it to. You can choose JSON or byte vector or whatever you want to serialize it into. And I'll leave the second type parameter free. And so here is where things begin to get interesting. So I know I'm just creating a literal integer here. But really, all I need to return is a string to lift into const, right? Because we ignore the second type parameter. And so what I can do is I can just call toString on the literal. Here, what's happening, let me finish writing this out, is I need to be able to serialize this add operation given the serialized form of the left and the right. And in the case of string, I can do something like paren l.get plus r.get. And then for square root, I'll do something similar. I need to somehow serialize the square root operation knowing the expression that I have so far. And I can do that with const and square root of i.get, I think. Ooh, what does it want? Oh, double. And now I can take my serialized form and get a string from it, like just passing program the serializer. And I need to get the value back out. And just to sort of drive it home, I'm going to print these results out. So result equals result, serialized. Oh, serialized equals serialized. All right, so we got the result, and we have the actual string form. And it's all with the same program. So in code that I've written at work, we have a DSL written in this style, and we allow users to write DSLs here directly in the source code, but also taking that exact same program without any changes, just also serialize it and dump it to disk, which is really cool, I think. And again, this is all possible because our DSL is parameterized over this type constructor. So calc here is a higher kind of type. And it gives us a way to sort of plug in a different kind of behavior we want. So everything I've showed you, I think, has been pretty straightforward, or pretty cool, I think. But you might have noticed that, like, in certain situations, I'm doing things like annotating the type here. And so, like, in the simple example, like with identity, I didn't have to annotate the type. But if I remove the type here, you'll see Scala C is not very happy with that. And I'm going to try to, will it let me? Cool. We get this error. No type parameters for method program exists so that it can be applied to arguments serializer. I'm going to go back here. And we did the same thing with this fold map, right? So I'm going to remove that. And we get the exact same error. No type parameters for method traverse exist so that can be applied to const. And I'm going to do the same thing with the first example, where we traverse with either. And I'm not going to show you the error, but the error is pretty much the same. So there's something going on here that I want to talk about, which is in the simpler use cases, we're able to use higher kind of types and just have everything be inferred and everything's nice. But it's sort of a pain to have to annotate types into less trivial examples. And this is actually a bug or a ticket that's been filed with the Scala compiler for, let's see, 4 or 5 years maybe. And so Miles talked about this at the keynote today. And this is like a very infamous ticket known fondly as SI 2712. And the problem here, so here's a sort of simplified example of what's happening. We're defining a method that's expecting a type constructor that takes one type and produces another type. And we're passing it a value that is of type that has 2 type parameters. So what the compiler is basically doing is saying, well, I expected a unary type constructor, but you gave me a binary one. 1 doesn't equal 2, so I'm going to fail. And you can also think of it as the choice is sort of ambiguous, right? Especially in this case. If the compiler were to infer what you meant, like which f you wanted to infer in this case, it could have chosen a partial application of the type constructor. Like you can think of it as a partial application of curried functions. This is partial application of type constructors. It could have partially applied from the left or the right, and it would have been, at least in this case, equally valid. So because it's ambiguous, the compiler is going to, you can think of it as the compiler saying, I don't know what to do, so I'm going to give up. And a similar situation is happening with traverse. Traverse f is taking a unary type. Traverse is taking a unary type constructor f. If we try to traverse it with an either, which takes two type parameters, 1 doesn't equal 2, the compiler fails. And so unless we explicitly annotate the types, the compiler doesn't know what to do. It turns out in this case, due to the way we've defined the applicative instance for either, the choices should be unambiguous, right? Only the first one should really work. If you substitute the second one in, I don't believe it actually type checks. So in this case, it's sort of unfortunate in that there's only really one choice, but just due to the way the compiler works, you sort of need to explicitly tell it, this is the partial application I meant, and it's not able to infer. And so the big difference here, because we had this parallel in the beginning between values and functions and proper types and type constructors. And this doesn't really manifest at the value level, because for one, we always explicitly tell it how we want to apply the functions, right? It's never the case right now where the compiler is able to infer programs for us, not yet anyways. And another thing is we have this different view of functions that we don't usually view type constructors. So in Scala and in languages like Haskell and even the foundation of the lambda calculus, we don't really have, you can view it as we don't really have functions that take multiple arguments. What we really have are curried functions that, and you can view functions that take multiple arguments as syntactic sugar on top of curried functions. So you can think of all functions as taking a single argument. And you emulate functions that take multiple arguments by treating them as functions that take one argument and return a function as a result that contains like the next parameters you need. And this is sort of how it's encoded in the lambda calculus, and this is how languages like Haskell and I think OCaml will work. But when we go into the type constructor land, we have these like binary type constructors or type constructors of 3 arguments. But we don't view them as type constructors that take one type and potentially produce another type constructor as a result. At least not in the surface syntax. But we can, in our minds, sort of pretend that that's the way it works. And so if we review type constructors as type-level functions that can be curried, then the choice for how we disambiguate the earlier examples becomes clear, right? We clearly always apply left to right, just like we do with functions. And this is how sort of Haskell does things in terms of resolving like the applicative instance for either. So going back to the traverse example, you could imagine that traverse is instantiated with these types, right? I'm saying either is going to be a type constructor that takes a type and produces a unary type constructor as a result. So the compiler should infer a traverse of either string, which will give it another type constructor, and then the remaining types are int and double. And that basically specializes traverse into a list of int into either string double and then either string list of b. Or I guess list of double, which that should be. And it turns out this is exactly what's happened in a recent fix that Miles put together earlier this year. So this was filed, let's see, April of this year, and this was met with a lot of thumbs up and smiley faces and celebration. This has been merged in Scala 2.12.0, which came out, I believe, 2 or 3 weeks ago. It's in the process of being backported to 2.11.9. And if you want to play with it now in 2.11, you can go to the type-level Scala compiler and play with it. You have to enable -y partial unification compiler flag to get it. But yeah, basically what the fix does is exactly what I've described. Is it assumes that the compiler is going to, when it meets a situation like expected unary type constructor and it got a binary one, it's going to try to partially apply it left to right. And it turns out that heuristic solves like 90% of the cases that people care about. It's important to emphasize that left to right is sort of a design choice. It just tends to be like the convention that people have adopted that we want to apply left to right. So the fact that the applicative and monad instance for either is right biased is influenced by this. So if instead like we decided to say infer right to left, then in order to make things play nicely, I believe we would have had to made either left biased instead. But left to right is what people tend to do, and that's the heuristic we've applied. So just to sort of drive this home, what I'm going to do is I'm going to go to my build. So I'm running 2.12.0 here. I'm going to enable Y partial unification, reload SPT, and compile. And everything works now. So I think that's really cool. This has solved many problems that many people have experienced. And that's all I had for you guys today. When the slides get put up, these will actually presumably link to useful things. That first one is a paper by Adrian, I think, that introduced higher kind of types to Scala. So thank you, Adrian. And other links are sort of learning more about why higher kind of types are useful. That second one is a blog post by Stephen Kompel on the type-level blog. And the latter three are sort of the tickets and the pull request and the explanation. That's all I had for you guys today. Thank you very much.